Next, we have Dr. Philip Mote from Oregon State University. Dr. Mote is the director for Oregon Climate Change Research Institute and Oregon Climate Services. Notably, he has participated on the Intergovernmental Panel for Climate Change since 2005. This morning, he'll be talking about what climate change means for California and how this connects to groundwater.
Thanks. Good morning, everybody. I should note, first of all, that California does not lack experts in surface hydrology and climate. You didn't have to import somebody from Oregon, but I'm pleased to be here, pleased to have this invitation. I actually grew up in Vacaville, just down the road here, and used to ride my bike with my best friend over to Davis because this was the big, exciting town that we could get to. And I also spent 2 years as a high school teacher in the Pajaro Valley in Watsonville, so it was kind of cool seeing that in the last talk. So what I'm going to do is talk about the interaction of climate change and surface water, and then the next talk is going to talk about the connection between climate change, surface water, and groundwater. I also want to note my co-author, Dennis Lettenmeyer from the University of Washington, who has, over the last 20 years, developed and applied a surface hydrology model, VIC, to a wide number of climate questions, and also a number of colleagues here listed at the bottom. So as we all know, this is a really huge drought situation that we're in. The period from January 2013 to present is the driest period on record in the state of California. It's also nicked us in southern Oregon as well, where several counties have experienced record low snowpack, and our governor also has declared a drought. I like this figure because it sort of emphasizes how sensitive the snowpack in the Pacific states is to warming. What this shows is the fraction of annual precipitation that falls as what we might call warm snow between 0 and -3 Celsius. And another way of putting it is, if we warmed up each grid point here by 3 degrees Celsius, those are the places that would see the largest shifts from snow to rain. So the West really lights up here, especially the mountains of the Sierra Nevada, Klamath-Siskiyou, Trinity, and then the Cascades up in Washington and Oregon. Those red colors indicating that roughly a third of the annual precipitation falls as warm snow. So these are places where we could see really large shifts in the timing of flows, because as you just saw in the previous talk, summers are extremely dry here, and when there is stream flow in the rivers, a lot of it originates as snowmelt, and not having snow, as we see this year, can have a huge impact on the summer stream flow. So this sort of sets the context for studying the interaction of climate and surface hydrology. This is kind of a cartoon illustration of what happens with a warmer climate. Basically, you get a higher snow line with less snow accumulation, and more of the precipitation in a given storm runs off immediately rather than sticking around for later. And this actually is a fairly sad and accurate representation of this year, that there's virtually no snow below about, as of April 1st, there was virtually no snow below 6,000 feet in California, below about 5,000 feet in Oregon. Almost 10 years ago, Dennis Lettenmeyer and I and a couple of colleagues wrote a paper on declining mountain snowpack in the western U.S. And on the right are the results of the VIC hydrologic model. On the left are observations. What's shown here in each panel is the linear trend over the 1950 to 97 period in the April 1st snow water equivalent, or SWE. These measurements were taken at monthly intervals, in some cases dating back to the 1930s or even earlier, by the U.S. Department of Agriculture, and in California by the California Department of Water Resources. And so what we did was simply plot those April 1 values for all the long records, and the red circles indicate decreases, the blue circles indicate increases, according to this legend here. Curiously, the Southern Sierras were one of the few places in the West to post increases over this period, and the hydrologic model shown here has a since it's a gridded hydrologic model, there is a colored square for each location where there was April 1 SWE, so the gray areas don't have any. But the redder it gets, the more the losses were. And so we can compare between these two panels and notice that there's a high prevalence of reds in the Pacific states, except, as I noted, the increase in the Southern Sierras. We are just in the process of updating this with data now through 2012, and so this is the same kind of plot, and again, a lot of red circles. Roughly 3/4 of the locations in the West have posted decreases, and California is no exception. And there's still some blue circles here, partly because the 1950s were a drought. So as if you start a linear fit at a low point, it's more likely to go up. I like this plot because this summarizes the relationship between those trends in the previous two figures and the temperature. So the y-axis in each of these panels is the winter. DJF is pronounced winter, in case you're not a climatologist. So the trends are binned by winter temperature. The red are from the hydrologic model, and the blue are from the observations. And so in the Cascades in particular, you see this really nice slope where at the warmest locations, and yes, we do get snow at places that are 3, 4, even 5 degrees Celsius in the winter. But in the warmest locations, you've seen decreases on the order of 100%. And as you get up toward the cooler locations, -5 Celsius and even colder, where there are very few to no observations, the trends have been very small. There is this little shift here between the model and the observations, which we never did figure out, but it's something we want to come back to as we update. As you get toward the dry interior and the Rocky Mountains, you don't see quite the same temperature sensitivity that you do in the coastal states. There's lots of other evidence that the surface hydrology is changing in response to warming. This is another paper from about 10 years ago, emphasizing that over this 1948 to 2002 period, the March flows have increased because snowmelt is occurring earlier, and then the June flows have decreased. So these pinks and reds indicate the trends in June flow are virtually all going down in the western U.S., and the blue virtually all going up. Snowfall equivalent, which is the ratio of winter snow to total precip, has also been going down, especially, again, in the Pacific states. The circles are statistically significant, and the size of the symbol indicates the magnitude of the trend relative to the standard deviation. So again, we're seeing this picture emerging of warming climate leading to less snowfall, earlier snowmelt, lower summer stream flow. Now, going into the future, before we talk about what the future climate will look like, we have to recognize that we can't really say how much greenhouse gas emissions will change over the coming 100 years. And so one way of dealing with that is to postulate a range of possible futures, and these are what are known as the representative concentration pathways. The concentration of carbon dioxide for each of these RCPs is plotted here out to 2100, although all of these scenarios go out to 2300, just in case anybody's worried about how their great-great-great-great-great-great-great-great-grandchildren will fare. The RCP2, well, let's start with RCP 8.5. This is a sort of unconstrained future, really enormous growth in greenhouse gases reaching over 900 parts per million. We're just a hair under 400 parts per million today. But notice also that this is showing no sign of leveling off. RCP6 is a somewhat more modest growth, but still more than doubling the CO2 in the atmosphere by the end of this century. RCP 4.5, you see the carbon dioxide is starting to level off by the end of the century. And this RCP 3PD, which is also called RCP 2.6, was designed to reflect a world in which we actually meet a target of 2 degrees Celsius global temperature change, which was articulated as a goal by former Governor Arnold Schwarzenegger and also by the European Union. So this, I mean, we might call this la-la land, because reaching stabilization of CO2 at 450 parts per million would require that over the next 2 decades, we dialed back global emissions to about where they were in the 1970s, and then kept going so that by about 2050, net emissions were 0. So that if anybody thinks that can really happen, talk to me. I'd love to share your enthusiasm. So for most purposes, scientifically, we tend to focus on the RCP 4.5 as a low but plausible future, and the RCP 8.5 as a upper bound. Over 20 global modeling groups have done simulations of the future. This is a map of the average temperature response averaged over all these for the sort of mid-21st century. And these are the changes in precipitation. So annual precipitation in California, averaged over all these models, does not change noticeably. Decreases in the south, very, very slight. But there is a general tendency towards slightly drier summers, although half of almost nothing is still almost nothing. We have a regional modeling experiment that uses volunteers' personal computers, and this is some very new work from that model. So this is the April snow water equivalent, the averages by season for each of these 3 states, and then the percent changes here. So decreases for California, the Sierras in blue, pretty large, 20-ish% through the winter, but getting much larger through the spring. Now on the Vic hydrologic model, I won't go into the details. It's a distributed model implemented in the western US at about 1/16th degree resolution. This is a simulation for the Sierras from 1950 to 2100 for a whole bunch of global models with a general decrease of about 50% in the April snowpack. And this is a set of maps averaged over models from some new work that Dennis Lettenmeyer and I are doing. And these are the 4.5 and 8.5 second half of the century. And then to see it more readily, these are the percent changes. So very large decreases in the spring snowpack, complete loss in many areas. Southern Sierras, high, cold, snowy, holding their ground better than most places. Soil moisture, springtime soil moisture actually goes up, especially in the Great Basin because of earlier snowmelt. Summer soil moisture goes down, especially in the mountains, because it's completely depleted a lot sooner. And I'll skip that. So the streamflow change, the response depends on the basin sensitivity and the climate forcing. So basins that are strongly snowmelt dependent, this is the Columbia Basin. Virtually all of the runoff comes in the spring snowmelt season. There aren't too many rivers like this in California, but up at high elevation, some streams show this. And so with a warming world, as you go farther into the later into the century, which is what the dash curves indicate, you get a decrease in that snowmelt peak. In a rain-dominant basin, of which many of the coastal basins are, and this is the Willamette in Oregon, very small changes, but a little bit of an increase in winter flow because of snowmelt and a decrease in summer flow. And then the most interesting ones are the sort of mixed rain and snow basins. So this is the Yakima River up in Washington. A complete change from a snowmelt dominated, the black, to a rain dominant in red over the course of this century. So summary, warming is inevitable. The amount is largely under the control of the human race. We could get a little bit of warming or a whole lot, but we will get some. Precipitation changes are uncertain. Some models say it'll get wetter, some say it'll get drier. The average is pretty close to no change. The hydrologic response to climate change is already underway. Changes in evapotranspiration, decreases in summer soil moisture in many places, large decreases in snowpack, and decreases in summer streamflow. So these will all help set the stage for what happens with groundwater, and the interactions are important. And of course, as these surface water supplies are depleted, and the reservoir storage is in many places not adequate to make up for these losses, and to store what's falling in the winter as rain, there will be more pressure on groundwater. Thank you.